Okay, folks, I'm going to try and get the hang of this time. I'm re-recording the end of chapter 7, so let's see if we can do it. I am going to refer to the notes, and I'm going to refer over here to the slides occasionally as well when I want a picture. Now, we finished with resonance, and so the next two topics have to do with different bonding theories. We're going to cover valence bond theory, we're going to cover Vesper, and then we're going to circle back around to hybridization. Now, valence bond theory takes into account atomic orbitals. We spent time before spring break talking about atomic orbitals. And the main ones that you have to keep in mind are S and P right now. When hydrogen comes together, right, each hydrogen has a 1s orbital. That's a sphere. And in that sphere, right, is an electron. That's the area where we're most likely to find an electron. Now, this image over here is referring to the electron as a wave instead of a particle. And the way these orbitals overlap is important. You either get constructive overlap that's going to lower the energy, or deconstructive overlap that raises the energy. This is what results in a bond, lowering the energy. Now, it's pretty simple here with hydrogen. Your two hydrogens get closer. Here we go. Let's go to the picture. And as long as the waves start to overlap constructively, then you form something called a sigma bond. So let's make the H's the nuclei. Those two sigma orbitals start to blend together, right? And you can see that electron density is focused over that internuclear axis, right? It's a head-to-head overlap, putting most of that electron density between the two nuclei. You can also see this with p orbitals. If you look at something like F2, fluorine has a full 1s, a full 2s, and then an almost full 2p subshell. So it is this half-filled p orbital that gets involved, right? P orbitals have kind of that figure 8 shape. So you have two fluorines that are going to start to overlap head to head. You're still getting the majority of that electron density in that line that connects the two nuclei. We're going to come back to that. So you have a picture of that here. All right, now the blue and the red are indicating the phases of the wave. So they use color usually, sometimes pluses and minuses, but to indicate that you're going to get constructive overlap. If you put blue to red, that would be deconstructive. But the way they're lined up, they're saying this is going to be favorable. We're going to get lower energy, and a sigma bond will form. Most of that electron density will be right there between the two nuclei. You can also get this head-to-head overlap between a sigma and a sigma and a p orbital. Ooh, I'm saying all sorts of crazy stuff. Let's draw it. Maybe that'll help. Between an S, that's from the hydrogen, and a p orbital, that's from the fluorine. Right? So you're still getting that head-to-head overlap, right, between the hydrogen and the fluorine nuclei. That's a sigma bond, right? Important vocab here. Direct overlap that concentrates that electron density on the internuclear axis. Now, when we get into, double and triple bonds, we get something called a pi bond as well. So all single bonds are sigma bonds. We want to know that for sure. All right, when we get into multiple bonds, we are going to come across something called a pi bond. So when we think about oxygen, it has a full 1s and 2s. It has one less electron than fluorine. So we have two p orbitals. And that's going to help explain something about the distribution of the double bond sets of electrons. Now, your p orbitals are in the x, y, and z axis. So let's focus on X and Y because that's easier to draw on the plane. If this is one oxygen, you have one pi orbital on the x-axis, one on the y-axis. You can get head-to-head overlap between the ones on the x-axis there. So that's a sigma bond. Double bonds all have one sigma. But then you're going to get overlap here. Oh, sorry. Let's see. Let's go to this. You're going to get overlap here above and below, right? You see where they're overlapping above and below from those parallel p orbitals. It's important to know pi bonds always involve p orbitals, right? Sigma bonds could have s or p or really any orbital as long as it's head-to-head. But with pi bonds, it's the parallel p orbitals. That's what's going to overlap. So you got electron density in the sigma bond between the two nuclei and from the pi bond above and below. So in a double bond, you get one sigma and you get one pi bond. With nitrogen, which has a triple bond, remember nitrogen has one less electron than oxygen. It's got a full 1s, a full 2s, and a half-filled 2p. So this is going to look messy. I'll try to put a picture in here on eCampus. Look for a picture of this. You've got your nitrogen atoms, right? You've got your sigma bond because the x-axis p orbitals are head-to-head overlap. The y-axis p orbitals give you that overlap above and below, and what's going to be hard to draw here is the z-axis, right? I'll put this in a different color. So if you can imagine, you've got a p orbital coming out towards you and into the paper, and so you're getting overlap out in front and behind, right? So it's almost like this, it's like a electron density all around. So you have electron density down the internuclear axis, the sigma bond, above and below the first pi bond, and in front and behind the second pi bond. What you need to take away from this is that single bonds are sigma, double bonds are one sigma and one pi, and triple bonds are one sigma and two pi. That'll let you answer some fairly basic questions, and I'm going to come back to hybridization, so let's skip that. We are going to see questions that might ask, how many sigma bonds, how many pi bonds in this random molecule? Well, every single bond has one sigma, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have 10 sigma bonds. And sigma bonds sometimes are shown with the little sigma symbol. How many pi bonds? Well, we have 1 in the double bond, and we have 2 in the triple. So there are 3 pi bonds. Sometimes you'll see a little pi symbol. You'll definitely have practice in your homework on that. Okay, I'm going to split this into 2 videos. The last video, we will do Vesper theory.